Hi, my name is Manish Gupta, and in this video number 200, I'm going to talk about PALO, which is a polyglot large multimodal model for 5 billion people, as it says, right? So let's first talk about what is PALO. So PALO is a multimodal large, a multilingual large multimodal model. Okay, so essentially it is multilingual and multimodal in nature. In fact, there are three different sizes available: 1.7 billion parameter, 7 billion parameter, and 13 billion parameter. And multimodality basically means that it can do visual reasoning, and multilinguality means that it can do visual reasoning in 10 different languages: English, Chinese, Hindi, Spanish, French, Arabic, Bengali, uh, um, Russian, Urdu, and Japanese. So which basically account for about 5 billion people. That is about 65% of the world population. Okay. So PALO uses a fine-tuned large language model to semi-automatically translate and adapt multimodal instruction data set from English to large to these target languages. Right. So one of the biggest problems in training multilingual multimodal models is lack of data, and they solve the problem by actually translating the English data to these languages. But of course, the standard translation faces some issues, and therefore they basically have an interesting recipe of actually doing some manual checks and then using a fine-tuned large language model to solve those translation issues. I'll detail about that in the next slide. Okay. So this essentially this step sort of leads to diverse instruction sets across languages, and that helps in improving performance, especially for the low resource languages. The basic architecture for PALO is Lava architecture. Of course, if you want a multimodal model, that's what is popular these days. So it uses the Lava architecture for the larger checkpoints, 7 billion and the 13 billion checkpoints. And for the smaller checkpoint of 1.7 billion parameters, it uses mobile VLM architecture. Okay. Now, why is PALO important? It's sort of important because of what you see, the performance that you see on the right side. So in this chart, each axis basically talks about a language, and they have also very nicely mentioned how many people are native speakers of that language, right? So as you see, English is 1.4 billion people, Chinese is 1.1 billion people, Hindi is 609 million people, and so on. Okay. What you also see are these four curves, basically, which show the accuracy of the model in terms of different languages, in terms of visual reasoning in those languages. Okay. So the largest or the best accuracies are, of course, observed using PALO. This is PALO 13 billion model. And second best is Lava 13 billion, so which is basically this curve. Of course, it's good for Russian, but it's really bad for Urdu, right? So really bad for Urdu and also really bad for Bengali, right? However, if you look at PALO, PALO is reasonably good in most languages. Of course, in some languages like Japanese and English, it's slightly worse compared to Lava, but I mean broadly, it performs nicely across multiple languages. Now, if you look at the smaller sized model, so mobile PALO is 1.7 billion parameter model. Of course, the accuracy is not that awesome, but well, the model is also very small. But if you really compare it with mobile VLM 1.7 billion, mobile VLM is not even visible. It's very, very close to that center. So essentially the accuracy is actually pretty poor compared to that. Of course, mobile PALO, which is the same size checkpoint, it's much better. Okay. So let's get into details of how is PALO trained. So first, let me just broadly talk about the architecture, and then I'll talk about the training data set and the training recipe and so on. Okay. So PALO follows a Lava architecture in that senses. So basically, of course, for visual reasoning, you actually have a question, you have an image and a text question. And what you want to do is to generate a good answer. So it's like a video, it's like an image-based question answering thing, right? So you take the image, pass it through a vision encoder, and then you get vision embeddings. You pass it through a projector so as to project it back, project it to a text embedding space, the language model's embedding space. For the text, for the question text, you basically pass it through a tokenizer and get those text tokens, which are concatenated with the visual embeddings, and then pass through the large language model. An autoregressive model then essentially generates tokens which are de-tokenized so as to get model response. A standard Lava-ish kind of architecture. Okay. Now, so in PALO 7 billion and 13 billion, the LLM, the large language model, is Vicuna, and they use a standard two-layer MLP projector, which has these two MLP layers with the GALU activation in between. But for mobile PALO, which is 1.7 billion parameters, you want it to be much more efficient and small in size. So the LLM which is basically used is mobile llama, which is very small. And then the projector which is used is basically this guy. It's a lightweight downsample projector. It basically comprises of several convolution layers, as you see. So there is pointwise convolution and depthwise convolution. So it sort of uses grouped convolutions in that senses. So or depthwise separable convolutions to downsample the image tokens that are coming in. Downsample the image tokens which are coming in, and thereby makes it actually much more efficient and faster compared to the MLP projector. Right? So it basically comprises of multiple convolution layers, thereby making it much more efficient. The vision encoder that they use basically is clip VIT model, clip VIT large model with 336 cross 336 pixel size. Right? So now let's talk about the data set. So how do you train PALO? So PALO has been trained using translated English data set, as I mentioned earlier, which is translated into multiple target languages. However, this translation leads to issues. So the translation is done using GPT 3.5 Turbo. It leads to issues like punctuation errors, grammatical nuances, translation inconsistencies, and gender usage issues. Right? So therefore, they basically take 1,000 conversations per language, and they ask native speakers to do a detailed review and correction of the translations. Okay, so 1,000 per language, that's quite huge in that sense. Is they use those 1,000 into 10 languages to fine-tune GPT 3.5 Turbo using OpenAI's fine-tuning API to translate this standard Lava Instruct 150K dataset. It's a vision language modeling instruction tuning dataset from English to target languages using this fine-tuned GPT 3.5 Turbo model. Okay. So, and that basically gives them a very reasonably good data set so as to fine tune the Lava model and get the PALO model out of it. Okay. So that's that. So now how does PALO perform? So they compare PALO with Lava model. Of course, we already know that PALO performs really well compared to Lava, but here are more detailed results. So as you see, PALO versus Lava, 7 billion checkpoint. So if you look at it on average across, so here are results for all languages, right? If you look at average across all languages, PALO basically gives you 10.8 points improvement. Even at the 13 billion range level, it gives you such a large improvement. And when you look at 1.7 billion parameter range, you actually still get pretty good improvements compared to mobile VLM. Now, so PALO not just performs good on average, but actually gives you better results for low resource languages across these different sizes, right? So in terms of high resource languages, yes, PALO actually leads to slight decrement. But if you look at low resource languages, the gains are crazy high. For the small language model, for the 1.7 billion parameter model, it actually gives you gains both for low resource and high resource languages. This evaluation that you see here was done on multilingual Lava Bench dataset, which basically has 24 images with 60 questions. So that's the dataset. The pre-training for the PALO model was done on CC 595K dataset, which is a subset of CC 3 million dataset. And while doing pre-training, you train the projector layer only while keeping the LLM and the vision encoder part frozen. And then fine tuning, well, for fine tuning, so Lava 3 and Lava 7 billion and 13 billion um, and mobile VLM, 1.7 billion, they are all trained on Lava, fine tuned on Lava Instruct 665K. So this is Lava, these are baselines, remember, okay? So these are baselines. However, the PALO models basically have been trained on, of course, the same Instruct 665K dataset, but it is also trained on Lava Instruct 150K that was obtained from the fine-tuned GPT 3.5, overall leading to about 2.1 million instructions. So it's basically trained on larger dataset, but also on dataset across multiple languages. So in this entire study, so what was high resource languages? Well, the high resource languages include English, Chinese, French, Spanish, Russian, and Japanese, which basically have a very good representation in the Lava pre-training itself. Okay. The low resource languages include Arabic, Hindi, Bengali, and Urdu. Now, while fine-tuning on these 2.1 million instruction data set, they freeze the projector and fully fine-tune. They freeze the, sorry, I think they freeze the vision encoder. They freeze the vision encoder and they fully fine-tune the projector and they LoRa fine-tune the large language model. So that's that. So they freeze the vision encoder, fully fine-tune the projector, and LoRa fine-tune the large language model. Okay. So in summary, in this video, I talked about PALO, which is a polyglot, a multilingual, large large multimodal model for 5 billion people. There are 3 different sizes of checkpoints and 10 languages that it supports. It uses a standard vision language model architecture, and it's basically fine-tuned by translating 150K instructions into each of the 10 languages, where the translations are obtained using fine-tuned GPT 3.5 Turbo, and 1K and about 1,000 human annotated conversations for each of those languages. So that's it about PALO. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.